Okay, so we are going to look at some problems today about predicate logic, some very simple problems, just to make sure that you understand everything about these concepts. So you are given the empty language. Can you construct all quantifier free formulas in the empty language? Do you remember what are terms? What are terms in the empty language? Only variables. Yes? Okay. So this is what we call L set. Yeah, L set is empty. So TL is all variables. TL set is the set of variables. Right. Okay. Then what are the atomic formulas in this language? What is F1? F1 is about relation symbols. But are there any relation symbols in this language? No. So then F1 prime is about equality. So with equality we can equate two terms. So what are terms? Right. So atomic formulas, atomic L set formulas are of the form xi equal to xj, and that's all. Yeah, nothing else can be done. And quantifier free formulas, what else can we use in quantifier free formulas? Negation and conjunctions. Okay. I mean this is just xi equal to xj, so we can only say this happens, this doesn't happen, this and this happens are conjunctions and are iterated conjunctions and negations of xi equal to xj. Okay, that's all we have. So this is a very boring language, but it expresses everything that you want to talk about sets. Yeah, for sets we can't really say much. And please note here that I am not talking about membership relation for sets. I am only ever considering equality of sets. Okay, so the next question is if our language consists of a single unary function symbol, then can you write formulas which express injectivity of this function? What is the definition of an injective function? F of x equal to Fy implies x equal to y. Now this is a formula. In our language it's a formula. Yeah, f of y. I'm going to write this, but this is not the final solution. So f of x is equal to f of y. This implies x is equal to y. This is a formula. But this only talks about, this can be either true or false depending on the value of x and y. But we don't want that. We want to say that the function is injective. So yes. And how do we change it to for all? X by W1 and Y by W2, and then we do it. Okay. So we are just going to write it directly. So for all W1, W2. Okay, so this for all W1 comma W2 is a short form for all W1 for all W2. Yeah, we just take, we don't write so many for alls. Yeah. F of W1 equal to F of W2 implies W1 equal to W2, and then we put a pair of brackets over here. Right. What about surjectivity? What is the definition of surjectivity? Y belongs to?
Some set X, then there exists another.
There is no set here. That's the X and Y are coming from where? X and Y are variables. This is a sentence. Every element in codomain has an inverse. Okay. What is the codomain?
Here it's a set is itself, but
So can we say for all
on
W1,
W2.
there exists a W2 such that f of W2 is W1.
Very good. So for all W1, there exists a W2 such that f of W2 is equal to W1. Now, when you, your confusion is well founded. When you interpret this sentence in a structure, for all W1 there is a W2 such that when you interpret this sentence in an L structure, this is our L. What will be a structure for this? It will be a set, non-empty set, together with a unary function. Okay, now when you interpret this, then it will say that the interpretation of that function, interpretation of the function symbol is surjective. Yeah, what is an M? I am going to write it in green. Yeah, L structure is M comma Fm, correct? And M is non-empty. And okay, we use this notation, yeah, curly M for this. So curly M satisfies this when what happens? How do we write it? Curly M, when does it satisfy this sentence? We saw that yesterday. For all is interpreted as for all, English language for all. Yeah, so this, if and only if, what happens? For all B in M, yeah, then I have to say something here. What should I say? M satisfies, there exists W2, then f of W2 equal to, so this is W1, so I should replace it with X, and this whole thing evaluated at B, the truth evaluated at B. Then this will be interpreted as if and only if for all B in M, there is A in M such that M satisfies f of y equal to x. This formula, the truth of this formula evaluated at, now I have to write B comma A. Yeah, we are doing it step by step. So this is just the reverse process of how we write formulas with quantifiers. We replace a free variable by a bound variable and then we put a quantifier. So here we do exactly opposite. We remove the quantifier and then we replace that bound variable by a free variable and then we write appropriately many tuples from the structure. Okay, and then if and only if, now you just have to substitute. Then the next step is that you interpret this f. So if and only if everything here such that, now you have to interpret, this is a formula of type equality. So this happens if and only if Fm of A is equal to interpretation of x at this, which is b. And then we are done. I mean, this is how we normally read it. Yeah, just to give you some practice, we wrote it again. Is this clear? Okay. So let's go to the next problem. It's again simple. If you are given a binary relation symbol only, yeah, I mean like orders or equivalence relations, then write down all L terms and quantifier free L formulas. What are L terms here? Just variables. Okay, so TL, I mean we call it TL odd, is equal to the set of variables. Okay, so TL odd is the set of variables. Then what are the atomic formulas in this case? Rxi xj, right? So atomic formulas. And very good. Rxi comma xj. Xi and xj could be equal. Yeah, nobody stops them from being equal. And xi equal to xj. And what are quantifier free? Are iterated negations and conjunctions. Of the above. So you can't really express much. Yeah, if you are working in natural numbers with respect to order relation, you can just say, well, one number is less than another, or it is equal, or it is not the case that this happens and maybe two of them happen simultaneously. But sentences give us a lot of power. Once we start using quantifiers, we can express a lot of complicated things. Okay, so in the same language, now express reflexivity. You all know the definition of reflexivity. When is R a reflexive relation? Tell me. When? R of A comma A. For all A. But A is not the right variable name. For all W. Very good. So for all W, what should I write? RWW. So simple. Okay. How do we write symmetry? For all W1, W2. RW1, W2 implies RW2, W1, and I should put a pair of parentheses around this. You can write down transitivity and trichotomy. Yeah, you all know what to do. Yeah, and you don't, but the thing that I am warning you about, if you do not use W's for quantified variables, for bound variables, you will lose marks. Okay, almost everybody is present here. So it is essential for this course to be precise. Yeah, so bound variables only by W and free variables only by X, Y, Z. Don't start writing for all A, R, A, A. You are not getting marks, because logic is all about writing. It's not that I am asking you anything difficult here. Right? Okay. So I think you can write down the remaining things in this question. Okay, so now you are given this new language which consists of a unary function symbol and a constant symbol. And you are given these three sentences. and you are asked that choose universe, so take n as the universe and find some interpretation of f and c so that these sentences are true. Can you think of anything? Successor and 0. Yeah, I mean, first try to read what it says. What does the first one say? Injectivity. Yeah, I mean, you already expressed injectivity on the first slide. Let me go back there. You said fx equal to fy implies x is equal to y. So, how is, this one for all w1, w2, this one. It only had one implication and not the other one. Are these two statements same or different? They are logically equivalent, modulo the fact that f is a function. Yeah, not otherwise. Okay. So the first one expresses injectivity. What does the second one express? The interpretation of C, yeah, that has no pre-image. So the interpretation of C doesn't belong to the image of F. Okay, and what does the last one say? About the complement. It's not 0. Don't talk about 0. Right now we are just interpreting a sentence. Yeah, so whenever it is not C, every element except C has a pre-image. Yeah, I mean these two sentences together say that it is surjective except for one element. The image only lacks one element and it is injective. Okay, so clearly, I mean, what I want you to do in this case is that verify, yeah, that n successor and 0 indeed satisfies these sentences. Can you tell me one other structure where this could be true? Can you think of any other structure where this is true? All these three sentences are true? In ordinals, which ordinal?
Success.
Yeah, this is an interesting discussion. Which ordinals? What if we take, I mean this is omega with shift operator and 0. What if you choose omega plus 1? Will this work? Because what will map to omega in omega plus 1? Yeah, it doesn't have a predecessor, so it doesn't work. So you need something where every element apart from 0 has a predecessor and a successor, both. What if I drop this condition and I just say it is surjective? Yeah, I mean I just say that it is injective and surjective. Then can you give me one such example? Integers, just integers themselves, right? Integers, the shift operator on integers, it satisfies this condition. It has successor and every element has a predecessor as well. So it extends on both sides. Now the thing that we need to do is take a copy of natural numbers and after that place a copy of integers and then define the successor function at 0. I mean 0 is in natural numbers. Now this structure will also satisfy all the things. Okay, what is happening? For natural numbers the successor is usual successor. For integers it's also the usual successor. But don't mess these things. Yeah, I mean this is disjoint union and it is order sum. One copy of natural numbers and every element in the copy of integers is strictly bigger than this copy of bigger than every natural number. Yeah, just like we do omega plus omega, right? So this is omega plus omega star plus omega. Omega star is the reverse. Yeah, so we also have something like this, and this is called a non-standard model of arithmetic. Yeah, there are infinitely many such. We will talk about them in due course of time. But this over here also we can do arithmetic. It's a non-standard model of arithmetic. Okay.
So,
Yes.
sir, can we take real numbers and take a function which maps 0 to 0 and every element is multiplicative numbers?
Yes, but then it won't satisfy this condition.
No, C also is 0. So.
C is 0, but C has a pre-image now. You defined it. You can think of something else, of course. Yeah, but this somehow expresses that we are infinite. Yeah, there is a function which is injective but not surjective, and it is from itself, like from a set to itself. Yeah, axiom of infinity, if you remember, then you might make sense of these three sentences. Okay. Let's do the next problem. A total order without endpoints does not have maximum and minimum elements. Express this fact in this as a sentence in the language of orders. So I'm going to just write down another problem here, that no maximum and minimum in L ord, just the language consisting of a binary relation symbol. Can you express that? No maximum yes, loudly.
Negation of there exists W1.
Okay, negation of there exists W1. Let's write it.
And for all W2, R of W1.
R of
W1.
W2 W1. For maximum or minimum?
Is it greater than or less than?
I don't know. Okay, so perhaps this sentence, does it make sense to everybody? When? Now you have to make sense of it. What should be R? If it is less than, then will this make sense? See, we are talking about maximum and minimum. So we are talking about a linear order. So all the axioms of reflexivity, antisymmetry, transitivity and trichotomy, they are already given to you. So no maximum is same as saying no maximal, and we saw the statement which says no maximal. Yeah, and R should be interpreted as strict order or weak order here. Weak order. Okay, so so there exists a W1 such that for all W2 R W2 W1, so this weak order will also work. Yeah, because W2 is less equal W2 itself, so weak order will work. Yeah, so interpret R as less equal And on the other hand, if you interpret R as greater equal, I mean, the only change you need to do for minimum is this. Just change the order of W1 and W2. That's for minimum. Without negation, it says there is a minimum, and with negation, it says there is no minimum. Now, just as a fun exercise, can we pass this inside? Pass this negation inside? What will happen? Negation there exists is what negation? I mean, this will be logically equivalent to for all W1, and then you push negation inside. So, negation there exists is for all negation. Okay? For all W2 are W1, W2. Then this is also further equivalent to negation for all is there exists negation. Very good. So, for all W1 there exists W2 such that negation are W1, W2. And this is what I wrote yesterday, if you remember. Yeah, I wrote it in this form. Okay. Yeah, another interesting question. Can you state Euclid's theorem on infinitude of primes as a single sentence? Yes, you have something?
Wait, this is an encoding for this because you're.
Well, let's make you write it and then we'll see if there is anything wrong. Can you please explain what you are writing?
Yeah, so this is saying if W1 is a prime, like this part, wait.
Mm-hmm.
And if W1 is a prime, then I'm saying there is a prime that's greater than it, so there will be infinity.
And how do you express something as a prime?
So if P divides it, then if A divides P, then A is equal to 1 or P.
If A divides P, and how do you express that something divides something?
There exists something it's a multiple of.
Correct. So using multiplication we can express division. Yes, please.
Then it should be
Right.
there exists W2, W3.
There exists
W2, W3.
there exists W2, W3.
No, this should be true for all A that divide P.
So for all W1, for all W2,
So it's not possible for all okay.
Like whenever there's an A that divides P, A is equal to 1 or A is equal to 2.
Okay, that will become false in that.
Yeah.
yeah. For all W2 there exists W3. If there is a W3 such that W1 is equal to W3, which means W2 divides W1, then W2 is either 1 or W1.
I think I got the parenthesis wrong.
Yes, I'm sure. It's very natural to mess up parenthesis in such a long expression. So that's why you define something called phi prime. Yeah, phi prime is a formula and then you express it in terms of phi prime and then you write down what is phi prime next. So always try to break it into pieces. You don't have to write everything in the same formula.
Yeah, and this is saying that prime is greater than the first number.
Right, prime is greater than that, and you also have to say that it is not equal to 0 perhaps. How will you, yeah, I mean, what is meaning of greater than in natural numbers with only addition and 0? That, I mean, A is greater than B if A is equal to B plus C for some non-zero C. That you have to express over here.
Wait, was the structure n plus 1 or n plus 0?
Let's just check. N plus dot 01, everything was given. You understand the idea? I mean, I'm not saying that this is entirely correct. There will be some parenthesis here and there missing or mismatched. But the idea is that you have to say that if I am prime, then there is another prime which is bigger than me. Yeah, so this is for all W1. If W1 is a prime, then there is a prime bigger than W1. And then primes are expressed in terms of division, and division is expressed in terms of multiplication. Yeah, we all know how to do this. Yeah, it's just that you have to make sure you write everything on the piece of paper correctly. Okay, so now I am going to pass it over. Yes, you have a question?
Sir, Euclid's algorithm doesn't state that if P1, P2, etc.
Mhm.
are prime, then the product plus 1 is prime. And that doesn't prove infinitely many times.
No, we are not trying to prove Euclid's theorem. We are just trying to write down that.
But that is not a statement of using Euclid's algorithm.
No, I said this is not the product. I said if there's any prime, there's a prime that's bigger.
There is a prime after that. The kind of thing that you are saying, that will say that if P1, P2, Pn is the list of all primes. Yeah?
So any prime, like not all primes.
All primes, then P1, P2, Pn plus 1 is also a prime. Yeah, so now that kind of argument is not expressible in first order logic, because it says P1, P2, Pn, any finite set of primes. But that n, P1, P2, Pn, what is that n?
Then you can take two primes also, then also it will work.
No, we don't want to do that. Yeah, you are going into the proof, but the statement only says this, that for every prime there is a prime bigger than that. The statement that you are talking about, I can explain it in a later lecture, why it is not first order expressible. If you cannot talk about arbitrary finite subsets of the set of primes. Huh? Subsets, yeah. Quantifying over subsets is not first order property. That's why we cannot do that.
But is this Euclid's algorithm?
This is not Euclidean algorithm. This is just the statement that there are infinitely many primes. And what you are referring to is the proof of this statement.
Okay, so I'm going to discuss question 8. It's part 1 of the. So this is the substitution theorem. So the question has two parts. First, you have to show that if you have Sy bar, which is a term, and Ti's of x bars are terms, then if you substitute the Ti's x bars in your Sy bar, then the resulting expression is also a term. So let's do that first. So when you're doing induction on terms, your base case will consist of your TE1 and TE2, and your induction step will be TE3. So TE1 talks about the variables. So if your Sy bar is simply the variable yi, then what will you get if you apply that term to any number of variables? It's projection. So what will it give you? It will give you the ith component, which is Ti x bar, which you are given is a term. It's given in the question. On the other hand, if it is a constant, if Sy bar is a constant, then whatever input you give it, it's going to be the same as a constant, which is also a term by definition of terms. Now, induction hypothesis, what do you have to do induction on? on the complexity of the term. So you build terms inductively, and so you have that notion of complexity of a term. So that's what you're doing induction on. So suppose that whenever your S dash y bars are terms of strictly lower complexity than S y bar, then your hypothesis is that S y bar of substituting Ti x bars in place of the yi's, that should also give you a term. Is the hypothesis clear? Okay. Then your induction step is TE3. You suppose that Sy bar is of the form f of Si y bar dot 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 Sm y bar, which would mean that these Si y bars are terms of lower complexity, and therefore you can apply your induction hypothesis. Then you know that each, then by the induction hypothesis, if you substitute Ti x bars in for y bar in each Si, then you will get a term. And therefore, if you just substitute this over here, by TE3, you know that if f is a function symbol and your f of T1 x bar dot 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 Tn x bar, if those are terms, then the resulting thing is also a term. So you use that TE3, and you get that this is also a term. Any questions?
What exactly is complexity?
So the definition of a term is inductive. You start from constants, variables, and then you start building things up using the function symbols. So that is like a rough notion of complexity. So you can say,
Like number of times a function is.
yeah, kind of. Yeah, you will have to refine that notion. So you can still use it without.
Number of times a clause in the definition is used.
Okay, the number of times that a clause in the definition is used. And yeah, so we don't need the exact definition to know what is going on in the proof. You just know that if you apply something to something else, then you get a term of higher complexity. Okay. So the second part tells you to show that if you take this term, we have just shown that this is a term, and you like take the M interpretation of that and you operate it on A, then you get this right-hand term. So again, base case is when Sy bar is, okay, I've switched the order of TE2 and TE1. Let's do TE1 first. If Sy bar is the variable yi, then St1 x bar, again, this is projection. So if you take this in M and apply it at A bar, then you will just get the ith term that will come out. And then this is TIM of A by definition of, applying it in a structure. And also, if you go the other way, so we have shown that this is equal to this, and also this is what? Again, this is just yi. So you get the ith term out, which is just TIM of A bar, right? Okay, what is TE2? If Sy bar is the constancy, then you take this value in M at A bar, this is just a constant, and then you just get C in M. And also the right-hand side is also C in M because this is just a constant. Any questions? Okay, so induction hypothesis, again the same thing. Suppose that the expression is true whenever, the expression is true for Sy bar whenever Sy bar is a term of complexity strictly lower than Sy bar. So you do the induction step, T3. Suppose that Sy bar is of this form. It's the function f applied to S1 y bar up to Sm y bar, which would mean that Si y bars are terms of lower complexity. So you can apply the induction hypothesis again. So then you start. You write the left-hand side, S of T1 x y bar up to Tm x y bar. You open that up. So S was simply of this form, so you just open that up over here. F of S1 of T1 xy bar up to Tm xy bar, dot dot dot, Sm of T1 x bar up to Tm x bar, and you take that in M at A bar. And so what does this mean? This will come inside, right? So you have to go to each term inside, I mean, we have just shown that this is a term, so we can do this. You have to go to each term inside and apply this same thing. So you get F in M applied on S1 of Tx bar dot 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 Tm x bar in M at A bar, and so on. And by the induction hypothesis, you know that this holds. So then you just substitute this expression everywhere. Here you substitute it everywhere. Now, what is this? You can see that this tuple belongs to m raised to m. So basically, it's like a sequence of elements in your M. So you can pull it out. And this is nothing but F of S1 y bar dot 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 Sm y bar in M applied at T1 A bar dot 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 Tm A bar. And now this is nothing but S of y bar. And so you can push this back in by substitution. Just substitute this inside this, and you get exactly what you needed. The left-hand side is equal to the right-hand side.
In the third last step, what we have done is that we have just said that we evaluated at this.
Yeah. Any other questions?
Okay, so what Nupur explained just now is the first part of the substitution theorem. So you are given one term in some variables, and you can replace those variables themselves by other terms. And then you get a new term. And then you have a dilemma. Yeah? How should I evaluate this new term? Should I evaluate the inner things first and then out, like inward out approach or outward in approach? Well, this particular exercise shows that they are the same. And similarly, there is a second part of substitution theorem, which is about truth of formulas. Yeah, so the truth of formulas, you can also do the same thing. If a formula is in variables x1, x2, xn, or y1, y2, ym, let's say, then you can replace those variables themselves by some terms, and then ask for the truth of that formula. Well, again, it doesn't really depend on what you do. Any way you evaluate it, it's going to be okay. Yeah, I mean, what is this? It's like saying, if I have the term x plus y, and I replace x with z square and y with w cube, then what will I get? Y square plus z square plus w cube. And then how do I evaluate z square plus w cube? Either you evaluate z square first and then w cube and then add, or you first do it from outside in. Both of the methods are valid. Okay. So make sure you solve the second half of the substitution theorem also, the truth of formulas. Now here is a very important and interesting concept in logic, and that concept is of a definable set. Definable sets actually tell us more about expressive powers of different languages. Yeah, so a set is said to be definable if it is precisely the set of tuples where a particular formula is true. So every definable set is associated with a formula. So let us read. If you are given a language L and you are given an L structure M, say that D subset of m to the power k, arbitrary power k is okay, is definable if there is a formula in k free variables, I mean context is k variables, such that for all tuples of length k, a bar belongs to D. It is in our definable set if and only if phi is true in M at a bar. Okay, so we are just trying to express our understanding of that set using a formula in that language. So, what about the first one? How do you say that something is a set of even numbers in natural numbers and only using addition? There exists a W such that okay. I mean maybe I will just use the letter plus here, yeah. So just tell me W plus W is equal to, now this is a formula in one variable x, one free variable. So if I substitute for x an even number, then this formula will be true, and if I substitute an odd number, then the formula will be false. So you understand that that is precisely the distinction between even and odds. So when you studied even numbers, you already were understanding this formula when you were a child, right? But now at this age you are understanding that this is expressible by a formula. Okay, what about the second one? If you are just given natural numbers and plus, how do you express odd numbers? Just one person at a time.
For every W, negation of W plus W is equals to x.
Okay. Yes.
So for there exists a W,
Uh-huh.
that W plus W bracket and some constant. Oh,
There is no constant. That's what I was waiting for. What he expressed is correct. Yeah. So negation of this basically. You just have to say it is not even. Once you express this, you are okay. But by this method, with just natural numbers and plus, you cannot express that it is a multiple of 3. Oh, sorry, you can express that it is a multiple of 3, but you cannot express that it is of the form 3a plus 1. Yeah, because there is no 1 in our language right now. So this is a limitation of this language. Okay, what about set of perfect squares in n plus 0? Now this is a catch, okay. This is not the solution, but I am going to write it down. There exists a W such that W plus W plus W, and now he is saying W times is equal to X. Did we ever allow this kind of thing? We can only add it to itself finitely many times. Yeah, and that finite number has to be predetermined. Yeah, it can be 100, but it cannot be a variable itself. So this is not right. But it is very difficult to express that something is not definable. For that, you have to understand all definable sets, find some common property, and then say that, oh, this set doesn't satisfy that property. So perfect square is an inherently multiplicative property. And multiplication you cannot express in first order language using using addition. I mean, addition is just a function symbol, think about it. Will you say, if I want to calculate pi into pi square, will you say add pi plus pi many times? Yeah, it doesn't make sense. So therefore this is not first order expressible, so it is not definable over here.
So still for natural numbers, that would not be the problem, right? Because you are composing a function anytime.
No, but how many times are you composing? That number, that parameter depends on the variable itself. Yeah, that is not allowed. In our formulas, how did we say f1 f1 prime, f2 f2 prime? sorry, F2, F3, and then F4 was that's it. Yeah, nothing else is expressible. That's it is important because of this reason. Okay, let's quickly cover this set of perfect squares in multiplicative language for natural numbers. Tell me. There exists a W such that W times W is equal to X. Yeah, this is easy. Set of non-negative real numbers when you don't have order, but you have addition and multiplication.
There exists W such that W dot W is equal to
There exists W such that W dot W is equal to? Same formula worked. You can see, being non-negative is same as having a square root in real numbers. Okay. So the set 1 comma minus 1 in Z dot 1.
X into x equals 1.
Yes, X into X is equal to 1. Very good. So this is simple. This is simply a solution set of a polynomial. What about this?
There exists W1, W2, W3, W4 such that W1
Very good. Perfect. And how did you think about this solution?
4 square theorem.
You knew about that already?
Yeah.
Okay. So there exist four natural numbers such that X is equal to sum of their squares. I mean, I am not writing the actual formula. When I am writing sum of 4 squares, I should be writing this bracket plus bracket plus. Maybe I should do that. Yeah. So this is, I mean, the solution to this problem is highly non-trivial. This is called Lagrange's 4 square theorem. So Lagrange had to prove that this is definable. Well, he never cared about definability, but this is the solution. So unless and until you know this theorem, you cannot solve this question. Yeah, that's why I wrote difficult in brackets. Okay, let's stop.